Okay, so this is the second online lecture, and so we're going to finish up talking about material from chapter 7. And so before we begin with new material, I just wanted to uh, make some comments about an error in a definition from the last lecture. And so if you go back to the definition for mutual independence that we use, so before I had this formula written out only for the list of all n events. So remember, we had a sample space S and we had a list of n events in the sample space, and we wanted to calculate we had this notion of mutual independence, which said that the probability they're going to be mutually independent if the probability of the intersection of all these events can be calculated by multiplying the individual probabilities of each event. And so in order to make this more useful, you really want this condition to hold not just for the whole collection, but also for any particular sub-collection of any size less than or equal to n, right? And so in particular, if you set m equal 2 here, you can see that there would only be some choice of two events that you're looking at the intersection over here. And so it's easy to see in that case that this formula is basically the same as the formula for pairwise independence. However, it's more general because here we want it to hold not just for two sets, but also for three sets and four sets and so on from the collection. Right, so I just wanted to point that out. Right. Okay, and so the first main topic we'll be talking about today is the binomial distribution. And so the binomial distribution is a probability distribution that arises in the sort of classically in the setting of something that's known as a Bernoulli trial. Uh, and so a Bernoulli trial is basically an experiment that has two possible outcomes. And we'll assume that one of those outcomes has probability P, and one of those outcomes has probability Q. So for example, maybe you have an old coin which is biased and lands heads 2/3 of the time. Right, so then we'll let P equal 2/3, which is the probability of the first outcome, which is flipping heads. And we'll let Q equal 1/3, which is the probability of the second outcome of flipping tails. And so note in particular that if I add P and Q together, I have to get 1 because I either have the first outcome or the second outcome. So the probability, the total probability adding them together should be 1 because at least we know for certain that one of the two will occur. Right, and so this is what's called an example of what's called a Bernoulli trial, is an experiment like this. Right, so you'll have an experiment with two possible outcomes, which you'll view as either success or failure. And P will denote the probability of having a success, and Q will be the probability of a failure. And since well, you're either going to succeed or fail, you should require that P plus Q is equal to 1 so that it makes sense from a probabilistic perspective. Right, and so sort of the situation that we're going to be considering is, well, what happens if you run a Bernoulli trial a few times in a row, right? So for example, let's say we work with this coin and we flip it 3 times in a row. Well, coin flips, each individual flip is mutually sort of a collection of coin flips is going to be mutually independent events because, right, for any given flip, it's not going to be influenced by what happened before the flip before it or the flip after it because you're sort of resetting everything when you flip the coin again. And so, right, so these sequences are mutually independent. And since they're mutually independent, we can calculate the probability of any particular outcome by basically just multiplying the probabilities of each individual flip. And so to clarify this, let's look at a particular example. So let's say we want to calculate the probability of flipping tails, then heads. Well, you can do this by taking the probability of t, which is q, times the probability of t times the probability of h. And so this reduces to q times p, which is 1/3 squared times 2/3. And so that would be the probability of this particular sequence. So one way to think about this is, well, basically in 1/3 of all scenarios, you expect to have tails on your first flip because, well, you have a 1/3 chance of flipping tails. And then so among those scenarios where you had tails on your first flip, you would expect in about 1/3 of those scenarios, you'll flip tails again. And then among all the scenarios where you flip tails twice, you expect in about 2/3 of those scenarios, you'll flip heads. Right, so if you quantitatively, if you write that out, you're really multiplying 1/3 times 1/3 times 2/3, which is this expression over here. Another way to think about this is, well, let's say I repeat this sort of experiment, the experiment meaning the trial where you flip the coin 3 times. Let's say I do this 27 different times. Well, you would expect that in about 1/3 of all those attempts, the first flip would be tails, right? And then among those outcomes where the first flip was tails, you would expect 1/3 to be tails again. And then among all those trials where you had tails twice, you would expect about 2/3 of those to be heads on average. And so that tells you that this ratio, which is 2/27, is a reasonable estimate for sort of the odds of getting this outcome. And you can model this more precisely mathematically using sort of the product distribution as we did in the weighted dice example, although I'm not going to go that much into detail for now. Right, and so what is sort of the general problem we're going to be considering? Right, so let's suppose we have some abstract Bernoulli trial, which we run n times. And so the questions that you can ask are, well, what are the probability that you have k successes where k is some integer less than or equal to n? Or equivalently, what is the probability that you have k failures, right? And so the main theorem that addresses this question is the following. So suppose I have a Bernoulli trial in the sense defined in the previous slide, with a probability p of success and a probability q of failure. And let's suppose that the trials are mutually independent. Right, and so the theorem says that the probability of k successes in these n trials is equal to this formula here. Well, I take the probability of a success and I raise it to the power k, multiply it by the probability of a failure raised to the power n minus k, sort of as we did in the previous example. But then I have to multiply this quantity by this binomial coefficient, which is n choose k. Right? And so this will give me the odds of k successes in n trials, this whole quantity here. And so one thing that's worth pointing out is that, well, by the binomial theorem, notice that, so we'll be able to use the binomial theorem to make sense of this a little bit more. So notice that, right, so if I add up the probability of a success plus the probability of a failure, or p plus q, remember that has to equal 1. And so if I raise 1 to the power of n, that's still just going to be equal to 1. So 1 is always equal to p plus q raised to the n. But then if I use the binomial theorem to expand this quantity over here, we get this sum, right, from k equals 0 to n of these individual terms, which we saw in the previous theorem. And so what this says is that if I take each of these terms and I sum them up as k varies from 0 to n, then they have to add up to 1. And we need to use the binomial theorem to see this. And so in terms of probability theory, what does this mean? Well, when k is equal to 0, this quantity tells me the probability, referring to the theorem above, this quantity tells me the probability of 0 successes in n trials. And then when k is equal to 1, this quantity gives me the probability of 1 success in n trials. When k is equal to 2, it gives me probability of 2 successes in n trials, and so on. And so I'm adding up here, as k varies, all the possible outcomes, right? You're either going to have 0 or 1 or 2 or 3, etc., successes, and right. And so since these are, you're sort of adding up all the possible outcomes, we should expect that the probabilities should sum up to 1, right? Because at least one of these, you're at least going to have some number of successes between 0 and n. And so if I add up the individual probabilities, we want this to be 1, or else we're not really working with the probability distribution. And so again, the key mathematical tool that allows us to verify that this is a distribution is the binomial theorem from the last chapter. Right. Okay, and so what I'll do now is just do a sketch of the proof of this theorem, which includes most of the main points, although I'll sort of sidestep some of the more sort of uninteresting sort of mathematical details. Right, and so one way to model this problem is to to sort of view the sequence of n trials as a sequence, say I'll call it bold x, x1, x2, x3 up to xn, where each term xi is either a success, which I'll call s, or a failure, which I'll call f, right? And so each xi is drawn from the set the set of two elements, which contains s and f, right? So xi is either a success or a failure. Sort of more precisely, you can model this using the sample space you get by taking the set, which contains s and f, and taking the Cartesian product with itself n times. And then this bold x is just an element of this Cartesian product, right? Right, and so now let's suppose we fix one such sequence of trials, this boldface x, and suppose that this sequence had k successes in it, and in particular, well, if it has k successes, it has to have n minus k failures. Right, well, as we sort of discussed before, since the trials are going to be mutually independent, it follows that we can calculate the probability of x by multiplying the probabilities of the number of successes times the probabilities of the number of failures, right? And so in particular, since we had k successes, when I multiply those numbers together, I'll have p appearing k times. And since I had n minus k failures, I'll have, in that string of numbers multiplied together, I'll have q appearing n minus k times. So notice this doesn't mean that for example, x1, x2, that the first k outcomes were successes and then the remaining n minus k outcomes were failures. It just means that of the elements in the list x1 through xn, k of them were successes and n minus k were failures. And so when I multiply out the probabilities, well, I'll have p appearing in that expression k times, and I'll have q appearing in that expression n minus k times. But of course, when I multiply numbers together, the order doesn't matter, so I can always just rearrange this expression to write it as p to the k times q to the n minus k. However, the main issue, though, is that, well, this can happen in several ways, right? It's possible that the first x1, x2 up to xk were all successes, and then the remaining trials were all failures. That's one possibility. But it also could be the case that maybe the first two were successes, and then you had a bunch of failures, and then a bunch more successes, and so on. And so you have to understand, well, how many ways are there that I can have k successes in the sequence of n trials? And so this is really just a combinatorial problem, which reduces to just asking, well, how many ways can I pick k elements out of n elements, right? Because I want to pick some subset of k elements and assign them all to be successes. And well, how many ways are there to do that? There's just going to be this binomial coefficient, n choose k, right? So there are n choose k ways to pick k of the outcomes to be successes. And for each such outcome, each individual outcome has this probability that we just calculated. So in order to get the total probability of having k successes, I just have to add up all these individual possibilities. And this is sort of equivalent to just multiplying the first quantity we derived by this binomial coefficient n choose k. And so that's basically where the theorem comes from. Right, so again, so if you have any fixed outcome where you have k successes and n minus k failures, the probability of that fixed outcome is p to the k times q to the n minus k. But you can have this scenario appearing in many different ways, which you can quantify using this binomial coefficient. And so when you add up all the different ways in which this can happen, this is the expression that you end up with, which is n choose k times p to the k times q to the n minus k. All right, so let's just quickly return to the weighted coin example and just apply this formula for a few problems related to this example. Right, so we have a weighted coin that will flip heads 2/3 of the time and tails 1/3 of the time. So there's two problems here. So let's suppose we flip this coin 6 times in a row. The first question is, well, what is the probability that you flip heads exactly 4 times? And the second question is, well, what is the probability that you flip tails exactly 3 times? And to answer both questions, we can just use the previous theorem. Right, and so notice in this case, we're running n trials with n equal to 6. And right, so we'll view the event of flipping a heads as a success. So we'll say P is 2/3, which is the probability of flipping heads. And Q is 1/3 is the probability of flipping tails, or the probability of a failure in this case. Right, and so the first question, what is the probability of flipping exactly 4 heads in the 6 trials? Right, well, right, in this case, I want 4 successes. So, right, I take P, which is 2/3 raised to the 4, times Q to the n minus K, which in this case is 2. And then I also have to multiply that by this binomial coefficient, which is 6 choose 4. And so if you plug this into a calculator, you can check that this is about 0.329. And so you have about a 33% chance of flipping 4 heads in this scenario. And so similarly for the second question, well, notice that the event where you flip 3 tails, since you have 6 flips overall, that's the same as flipping 3 heads, right? It just happens to be symmetric in this case. Right, and so in this case, we'll just use the formula again, but now with k equals 3, because we're looking for the probability of 3 successes in 6 trials. And so if you use the formula, you get this expression over here. And if you plug that into a calculator, it's about equal to 0.2195, or you have about a 22% chance of flipping 3 heads in this scenario. Okay, and so that's sort of the main point that I wanted to make related to Bernoulli trials. And so just again, just a bit of terminology. The distribution that we're using here is usually called the binomial distribution. Binomial distribution assigns probabilities to having k successes in n trials in a Bernoulli trial setup. And so one key point to make again is just that this is a situation where some of these combinatorial identities we saw in chapter 6 are actually applied in the real world. I mean, Bernoulli trials sort of show up all over the place. So there are some more complicated examples of distributions that sort of involve some of the other combinatorial identities we looked at in chapter 6. So what I'll probably do is maybe send you an email or a link with some more information about that, just so you can have some more examples of sort of where in the real world some of these combinatorial things we studied in chapter 6 are actually applied. But this example that we just saw, the binomial distribution, is one very important example. Okay, and so the next main topic is Bayes' theorem, which is basically the whole content of chapter 7.3 in the book. And so Bayes' theorem is a very powerful tool that gives you a way to calculate certain conditional probabilities. And so what I'll do first is begin with a motivating example, which will sort of outline a particular problem, which can be solved using this theorem, which is called Bayes' theorem, which I'll turn to after this motivating slide. And so the problem is the following. So let's say we have an incoming email being sent to us, and we want to use our computer to try to detect the probability that this email is a spam email based on a collection of words that appear in the email. Right, so maybe this set W of words is something that is some collection of words that have been sort of known in the past to very frequently appear in spam, and we see that some of these words are in our email, and we want to sort of try to understand, given that these words are in email, what's the odds that the email is actually spam. And so there are a few pieces of information that would help us actually solve this problem. So the first bit of information is, say, the percentage of overall incoming messages that are known to be spam, independent of what words are in them. And so this is something that you would measure experimentally, right? This would be some bit of empirical data, which we're assuming maybe we know this, right? We just sort of look it up, like how many overall messages, emails that are sent are spam. The second bit of helpful information would be, well, let's say we happen to know the percentage of messages which are spam and which also contain words from the set W. Right, so for example, if say words from W appear in like 90% of all messages which are spam, and also words from W are appearing in the email we're receiving, then maybe there's a pretty high chance that the email we're receiving is spam. On the other hand, it will also help to know the percentage of messages which are not spam, which also contain words from our set W. For example, maybe like some large, maybe like 50% of messages which are not spam contain words from W, and maybe 50% of messages which are spam contain words from W. Maybe in that case, just because W appears in a lot of spam messages, it doesn't necessarily imply that the email we receive will be spam, right? So this is another bit of information which will be helpful to answering this question. And so what is Bayes' theorem? Well, Bayes' theorem is sort of a mathematical tool that allows us to give a reasonable solution to the problem I've just outlined, given a collection of data that looks like this list over here, right? So you'll have to assume that you know some certain amount of empirical data, which you presumably collected out in the world at some point, which you're using to analyze the problem. Right. And so here's the formal mathematical statement of the theorem. And so we'll have some sort of abstract sample space with a probability distribution, and we'll have two events in the sample space, both with non-zero probability. So Bayes' theorem is a statement really about conditional probabilities, and it reduces to this formula over here, which says that I can calculate the probability of F given E by calculating this expression on the right-hand side, right? Probability of E given F times probability of F divided by the sum of these two terms over here. Right, and so if I sort of analyze this a little bit more, what does this formula really tell us? Well, suppose we know the probability that a certain event F occurs, and suppose we also know these two conditional probabilities, right? The probability of E given F and the probability of E given the complement of F, or given that F does not occur. Right, and so one thing to point out is you could raise the issue, well, there's also probability of the complement of F that appears in this formula, but remember that as long as I know the probability of F, I can calculate the probability of the complement of F just using this identity over here, right? So if we know probability of F, we also know probability of complement of F, right? And so if we know these three pieces of information, Bayes' theorem tells us that this is enough to calculate the probability of F given E, or to calculate the conditional probability on the left-hand side. And so if you go back to the example that I outlined on the previous slides, these sort of, we're gonna interpret this where the quantities on the right are sort of the assumed bits of data that I listed out before, and we're going to be trying to calculate like the probability that a given email is spam on the left-hand side, relating it to those quantities on the right-hand side, which we'll see on starting on the next slide. Right, and so how do you actually prove this theorem? So the proof is not so interesting, so I'm going to omit it from the slides. The way you prove this is basically just on the right-hand side, just plug in the formulas for the conditional probabilities and sort of do some algebraic calculations, and you'll see that this complicated expression will simplify to the formula for the probability of F given E. And so if you want, maybe you can pause the lecture and just try to do that exercise to review the definition of conditional probability. And if you get stuck, you can also just look in the textbook where it's written out in detail. And again, so since it's just sort of an algebraic calculation, I'm not going to include it in the slides. No. Great, but what we will do now is turn back to the spam email example and try to use this theorem to understand that problem better. Right, so let's suppose, right, so what I'm going to do is maybe simplify the problem just a little bit from the from how we saw it on a few slides ago. So let's suppose we receive one incoming email and we want to know whether or not this email is spam. And moreover, let's suppose that there's a certain flagged word W, which we've noticed appears in the email. So I'm not considering a whole set of different words, but let's just say there's just one word W, which is a flagged, potentially spam word that has appeared in the email. So what we want to do is calculate the probability that this email is spam, given that W is in the email, right? So notice this is a conditional probability because the conditional effect is that we're assuming W is in the email. And so what we want to do is calculate this conditional probability, assuming some other collection of empirical data that we know independently. And so we're gonna do this using Bayes' theorem. And so what I want to do is just begin with sort of the formal setup. And then we'll see how to use Bayes' theorem. And so sort of like a lot of mathematical modeling problems, what you really want to do is make sure you sort of carefully label everything that you're going to work with before you start trying to write down formulas and things like that. Right, so let's suppose we have some set B of messages which are known to be spam messages, and another set G of messages which are known to be not spam. And so we'll assume that these sets have been given to us, right, sort of maybe through several years of experimental measuring on the internet, collecting data on the internet, something like that. Right, so B would be for bad messages and G is for good messages. Right, and so given these two collections and given our fixed word W, we're going to let n sub B of W be the number of messages in B that contain W. So this is sort of like the frequency of bad messages or spam messages in which W appeared. On the other hand, we'll let n sub GW be the number of messages in G containing the word W. So this B should be a G, this is a typo. Right, so n sub G of W will be the number of messages in G that contain the word W, which has the interpretation of being like the frequency of good messages which were not spam that contain W. And so notice that both of these quantities are actually important for our problem, because let's say that both of these frequencies are about the same, right? So maybe that sort of has the sort of loose interpretation that you have a 50% chance that it's spam and a 50% chance that it's not spam. Well, in that case, you don't want to hide the email away in a spam folder because there's a pretty strong chance that it's not spam, right? So both of these quantities are relevant. Right, and so using these two quantities, again, which we're assuming is something that's been given to us through data collection or something like that, we'll construct these two, which I'll call empirical probabilities because they're based on some measurements which we're assuming. So I'll define a function P of W to be the ratio NB of W divided by B, which is sort of like the fraction of bad messages in which W appears. And then I'll also define Q of W to be N sub G of W divided by the cardinality of G. And so this is like the fraction of good messages in which W appears. Right, and you want to think of this is sort of like the ratio of words in B or G that contain W. Not necessarily, I mean, more precisely, it's really messages that contain W, but that's the main idea. Right, and so we want to think about this in terms of conditional probabilities, so we have to precisely define, well, what events are we working with? So I'm going to let E be the event that the email we received contains W, which is something we're assuming, right? So we're assuming this event E occurs. And I'm going to let S be the event the email is spam, right? So you shouldn't get this confused with S being a sample space. In this case, S is not a sample space. The sample space is some sort of abstract collection of emails, which we're not going to worry about too much for this example. But S is going to be the particular event that the email we receive is spam. And so what do we really want to calculate? Well, we want to calculate the probability of S given E, meaning we've received this email and we want to know the probability that this email is spam given that it contains W. Right. And so what we'll do now is plug this into Bayes' theorem and use the Bayes' theorem to analyze this probability further. Right, so that's what we'll do now. Right, so by Bayes' theorem, we have this sort of complicated looking formula. So the probability that our email is spam, given that W appears in the email, can be computed by looking at this messy fraction. And so what we're going to do first is add an additional assumption that makes this a little bit easier to work with. In particular, we're gonna assume that we know the probability of S and the probability of the complement of S. In particular, we'll make sort of the empirical assumption that our email S is equally likely to be spam as it is not spam. So maybe we're assuming that half of the emails sent in the world every day are spam and half of the emails sent in the world are not spam. Maybe that's not so accurate, but it's maybe hopefully a reasonable assumption to make, since, I mean, at the end of the day, we're just trying to come up with an estimate. We're not trying to prove that this is the exact probability. We just want sort of a reasonable guess. And so making this sort of reasonable assumption, if they're equally likely to occur, then they both have to have probability 1/2, right? And so, right, I can replace P of S, and P of S bar by 1/2. And then notice that those terms will just sort of cancel out from the fraction. And so the formula will simplify to this slightly easier expression. Oh, one thing that I want to point out that I forgot to mention a few minutes ago is you shouldn't confuse this P with the function P of W. So I realize that this is sort of bad notation because this function P of W is a different object than the probability distribution we're using here. And so I would have actually changed the notation, but I wanted these slides to be consistent with the notation that's used in the book. So, I mean, it should be clear from context. Whenever you see P of W, that's this function, and otherwise it's our probability distribution. But I apologize that maybe this notation is a little bit confusing. Right, and so we're at this point where we've canceled out the terms involving P of S or P of S bar. And so the conditional probability we're interested in, we can calculate just as the probability of E given S divided by probability of E given S plus the probability of E given the complement of S. And so now at this point, we need to sort of interpret the quantities appearing on the right-hand side in terms of the data we've been given. And so we're going to make two estimates. So the first estimate is that the probability that the message contains our fixed word W, given that it is spam, is the function P of W, right? And so this is what we're going to plug in for probability of E given S, right? Right, and so how should you think about this? Well, what is the probability of E given S? This is the probability that our word W is appearing in the email, assuming that we know the email is spam. Well, what is the set B? B is sort of the collection of all known spam messages, and this is sort of measuring the frequency or the ratio of the percentage of those messages which contain W. And so this fraction is a reasonable estimate for the probability that W is in our email, given that it's spam. And similarly, so a reasonable estimate for the probability that our message, the probability that our email contains W, given that it's not spam, which is this conditional probability over here. A reasonable estimate for this quantity is the ratio Q of W, right? So the number of messages which are known to not be spam that contain W divided by the overall number of messages that are not spam. Right, so this function Q of W is a good estimate for the probability that our email contains W, which is E, given that it's not spam, which is this conditional probability. Right, and so we're going to plug in this function P of W for probability of E given S, and we're going to plug in this function Q of W for probability of E given not S. And so if we do this, the formula reduces to the following. So the probability that our message is spam, given that W is in the message, can be calculated just by looking at this fraction, right? So we would have to calculate P of W and Q of W and just calculate this fraction, and this would give us a good estimate for the conditional probability. Of course, as I said a few minutes ago, this is all just sort of an estimate. Like, we're not sort of rigorously proving that this is exactly the precise probability. But in the real world, it's usually good enough to just have sort of an estimate and not have everything be as accurate as it can possibly be. Right, and so again, this is just sort of repeating what I just said. So assuming we know these two functions, for example, you would have a good guess of these functions from some experimental data that you've collected on the internet. We would have a good guess about the probability that our email is spam, given that W is in the message. Right, so let's just do a quick example where we apply sort of the analysis that we've just done. So suppose that we found by collecting data that the word gift appears in 200 out of every 2,000 messages that are known to be spam. And suppose we also know that the word gift appears in 5 out of every 800 messages that are known to not be spam. Right, and so the question is, well, what is a good estimate for the probability that an incoming email we receive is spam, given that the word gift appears in this message? Right, so this is exactly the sort of problem we've just been sort of analyzing in a little bit more of abstraction. Right, and so what's the solution? Well, the solution is we'll just sort of interpret this using Bayes' theorem and then plug in this formula that we just derived. Right, so we want to calculate P of W and Q of W. So to calculate P of W, well, we're told that 200, right, so this number 2,000, you have 2,000 messages that are known to be spam. So the cardinality of B in this case, which are the bad messages, is 2,000. And we know that the word gift, which is a W in this case is the word gift, we know that this appears in 200 out of those 2,000. So the function P of W is going to be 200 divided by 2,000, which is 0.1. On the other hand, we're also given that for every collection of 800 messages which are good, we know that the word gift appears in about 5 out of every 800 good messages. And so the function Q of W, again, where W is gift, is the word gift, is going to be about 5 divided by 800, which is about 0.00, or exactly equal to 0.00625. Okay. And so now we want to know the probability that our message is spam, given that W is in the message. Well, we have a formula on the top of the slide that tells us how to calculate that, assuming we know P of W and Q of W. And so if I plug these in to the above formula and calculate it, I see the conditional probability that our message is spam is about 94%. Right, so given this data, we would say that there's about a 94% chance that the message is spam. And this is related to the fact that the word gift appears in a lot of spam messages, although you have to modify that to take into account that there are also some messages which are not spam in which the word gift appears. Okay, and so, right, so that's about everything I wanted to say related to Bayes' theorem. So if you look in the textbook, there are some more, you'll be able to find some more examples similar to what I just did involving spam filters. If you want some some more examples to look at. And so there's also another, so this is one of the major applications of Bayes' theorem, which is sort of detecting whether or not an email is spam. And so how would you actually use this, right? Maybe like, for example, Gmail will cut a threshold, like if this number is, say, above 0.9, or if the probability is more than like 90%, then it puts it in the spam folder or something like that. That would be sort of one simple way to do this. I mean, I'm sure the algorithms that are used on Gmail are a little bit more complicated than this, but this is sort of the mathematical foundation for how that analysis works. So there's another important application of Bayes' theorem involving medical tests and trying to understand the odds of a test having like a false positive or a false negative or something like that. And there's a whole discussion about this in the textbook, which I think if you're interested, it would be worth reading. So you sort of have another example of where in the real world Bayes' theorem is applied. It'll also give you sort of more practice understanding Bayes' theorem. Okay, and so, right, so that's it for chapter 7. So in the next lecture, we'll move on to chapter 8.